Hello, everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to continue with the chapter Biomolecules. And since we have already discussed what are the various types of carbohydrates in the classification of carbohydrates, we have talked about monosaccharides, oligosaccharides, and polysaccharides. Now we are going to be starting one by one with various saccharides that we have to discuss. The first one that we are taking up is glucose, and in this particular lecture, we'll be discussing the preparation as well as the structure of glucose. Before we begin, a piece of information for you. You can use the coupon codes Mission JEE or Mission NEET while you enroll at First Online University for Mission JEE or NEET in order to avail good discounts. Let us now begin with the preparation and structure of glucose part 1. Now, when we talk about glucose, it is the most it's like the most abundant naturally occurring sugar. And we have already discussed that it is a very common source which is found. See, other fruits have fructose, okay? The sugar which is present in fruits is fructose, except for grapes which have got glucose. So this is an important information to note here, that this is the reason why sugar patients or patients who are diabetic, they are advised not to consume grapes. They can consume any other fruit, yes, apart from those which are very sweet, but they cannot specifically consume grapes because grapes do not have fructose, they have glucose, and glucose is something which diabetic patients cannot consume because they have less amount of insulin being produced that can actually act upon these glucose molecules entering into the body through the digestive system. Apart from grapes, honey and human blood also has glucose present in it. Okay. Now, when we talk about the preparation of glucose, there are two ways. One is commercial method, the other is laboratory method. Let us first discuss the lab method or the laboratory method. Now, we know that cane sugar is one way. So, when we have sucrose undergoing hydrolysis, it will give me glucose plus fructose. We have already studied that sucrose is a disaccharide, and on hydrolysis, it is going to give two monosaccharides. One is glucose, the other is fructose. So glucose is produced by the hydrolysis of sucrose. This is the chemical reaction that is involved, and in hydrolysis we are making use of H2SO4 or HCl, and sucrose is also known as cane sugar. Now the question is that both glucose and fructose are going to be formed. How can we actually separate glucose from fructose in the product? Okay, now this can be done while cooling. Okay, when we get the product and we cool the reaction mixture now, then alcohol is added to this reaction mixture. Glucose, being insoluble in alcohol, will crystallize out first, and those crystals can then be separated out. Since fructose is more soluble in alcohol, it will remain in the dissolved form or it will remain in the solution. So those crystals that we get are those of glucose, which we can actually filter out. Now, next method of preparation is from starch. So when we are taking excess of sulfuric acid, that can actually be neutralized by adding chalk powder towards the end of the reaction. The colored impurities are going to be removed by adding activated charcoal in this procedure that we are going to discuss, and glucose crystals are removed by cooling. Now, when we talk about the structure of glucose, glucose is an aldohexose. Now, what do we get from aldohexose? Aldo means there is aldehyde functional group that is present. Hexose means there are 6 carbon atoms present. And it is also known as dextrose. Now, why dextrose? Because it is dextrorotatory in nature. This you will study under stereochemistry, where you will be talking about optical isomerism. But I'll just tell you here right now, when we talk about sugars, when you see the last chiral center, now what is a chiral center? A chiral center is the one which has 4 different groups attached to it. Okay. When we talk about a chiral carbon, so when it has 4 different groups attached to it, it will be called as the asymmetric center or the chiral center. Now, when this chiral center Okay, so when we talk about glucose, the second last carbon atom, which is the last chiral center, when it has OH group present on the right hand side, it is called dextrorotatory. When it has got OH group present on the left hand side, it is called levorotatory. And if you remember, we have seen the structures of glucose and fructose. It was like all the carbon atoms except for the third carbon atom had OH group on the right hand side, which means that the fifth carbon atom, which is the last chiral center, will have OH group on the right hand side only, and on right hand side it will be dextrorotatory. Therefore, glucose is also known as dextrose. It is the monomer of many large carbohydrates like starch, cellulose, etc. And it is probably the most abundant organic compound on earth. It was assigned the structure given on the basis of the following evidence. Okay, so it was assigned a particular structure which is like this that has been mentioned. And this structure was actually assigned based on a lot of evidences which were found by performing various experiments in the lab. Its molecular formula was found to be C6H12O6, and on prolonged heating with HI, what happens is the N-hexane form is going to be obtained, suggesting that all the 6 carbon atoms are present or linked together in a straight chain. There is no branching. Why? Because we got N-hexane as the product, and N-hexane means there is no branching that is present. So when we have glucose, CHO, CHOH whole 4 and CH2OH linked together and we add HI to it and heat it, what do we get is N-hexane. And this means that all the 6 carbon atoms are present in a straight chain form. Then the second reaction which was carried out was the reaction with hydroxylamine, where it formed oxime as the product, and it also adds a molecule of hydrogen cyanide to give cyanohydrin. These reactions confirm the presence of a carbonyl group in glucose molecule. So how did we get to know that there is a C double bond O group present? Through these two reactions. So when we have CHOH whole 4 and CH2OH and we add hydroxylamine to it, what we get is CH double bond NOH, CHOH whole 4 and CH2OH. Okay, this is the moiety that we get. Now, this is glucose oxime. Now, when this glucose oxime was actually, okay, so that's one reaction. We get glucose oxime because there is CHO group present. Secondly, when we add HCl to it, what we get is cyanohydrin. Now, this glucose cyanohydrin indicates that there was again a C double bond O group present. So, these two reactions will confirm the presence of C double bond O group in the structure of glucose. Okay, so now we know that two things we know. From the first experiment, we knew that since we are getting N-hexane, so it is a straight chain of 6 atoms, 6 carbon atoms aligned in a straight chain. The second reaction or the second experiment confirmed that there is a C double bond O group that is present in the structure of glucose. These reactions are very simple. You do not have to cram them. You can easily produce them. Next reaction was that glucose is going to glucose gets oxidized to 6 carbon carboxylic acid, which is known as gluconic acid, on reaction with a mild oxidizing agent like bromine water itself. This indicates that the carbonyl group is present as an aldehyde group. Okay. So if we have this reaction being performed on glucose molecule when we add bromine water to it, we see that HCHO group, that is aldehyde group, it will get oxidized to COOH group, which gives us gluconic acid as the product. So this confirms that there is an aldehyde group present. On oxidation with nitric acid, glucose as well as gluconic acid both yield a dicarboxylic acid, which is called saccharic acid. And this indicates the presence of primary alcohol. So now, apart from the fact, so now this is the fourth experiment. The first one was that it is a straight chain with all the 6 carbon atoms aligned in a straight chain. Second was that there is a C double bond O group present. The third experiment confirmed that the C double bond O group was actually an aldehyde, not a ketone. And now this fourth reaction or the fourth experiment is confirming the presence of primary alcohol. That is the last carbon atom actually is a primary alcohol, right? So oxidation will give dicarboxylic acid from both glucose as well as gluconic acid. Okay, that means we are getting saccharic acid from gluconic acid also and from glucose also. Okay, because there is complete oxidation that is going to take place. Now, based on this, let's quickly have a look at few MCQs. Glucose commercially prepared from sucrose, cane sugar, both NV or starch. So we have seen that laboratory method involves the use of sucrose or cane sugar. One is the same thing, but commercial method involves the use of starch. So option D is the correct answer. Next question is hydrolysis of sucrose produces glucose, fructose, both A and B or maltose. So we have seen that sucrose is a disaccharide and it will get hydrolyzed into two units of monosaccharides. One is glucose, the other is fructose. So option C is the correct answer. Next question is which one of the following is not a sugar? Sucrose, glucose, fructose or cellulose. So we have seen that there is a sugar and there is a non-sugar and it is cellulose which is not a sugar. So option D is the correct answer. Next we move on to preparation and structure of glucose part 2. Now here we have already discussed till here we know that it is a straight chain. It has got a C double bond O group which is nothing but an aldehyde group and there is a primary alcohol present. Now, further reactions or experiments will tell us that what is the rest of the structure of glucose. So, acetylation of glucose with acetic anhydride gives glucose pentaacetate, which confirms the presence of 5 OH groups. So, the fifth experiment will tell us that there are 5 OH groups present. The last one we have already identified is actually a primary alcohol. Now, there are 4 other left. That means the 4 carbon atoms, apart from the one which is CHO, will all of them have an OH group each. Okay, so 5 OH groups should be attached to different carbon atoms. So when we have this particular structure, acetic anhydride is going to yield this compound, which is nothing but glucose pentaacetate. What is happening here is wherever there was an OH group present, it is turning into OCOCH3 group, OCOCH3. That is nothing but glucose pentaacetate. Then now we know what all is present, but the exact spatial arrangement of these OH groups was actually given by Fischer after studying many other properties, and its configuration is represented as I. So gluconic acid, not I, it's Roman numeral 1. So gluconic acid is represented as 2 and saccharic acid as 3. So glucose is basically having this configuration. So this was actually given by Fischer based on a number of experiments. What experiments he performed, etc. That is not important as of now. We need not go into details of those. But he actually gave this structure, which we know is the structure of glucose, where only the third carbon atom will have OH present on the left hand side. All the rest of the carbon atoms will have OH groups present on the right hand side. This is the structure of glucose. Then the derivatives of glucose are gluconic acid, where CHO group just has been oxidized to COOH group, rest is the same. And saccharic acid is where you have both the CHO group as well as the primary alcohol, that is CH2OH, having been oxidized to COOH group. Now, glucose is correctly named as D plus glucose. D stands for dextro. Okay, that I've already told you. D before the name of glucose represents the configuration, whereas, so plus sign represents dextrorotatory nature of the molecule, and capital D is representing the configuration. Now, it may be remembered that capital D and capital L have no relation with the optical activity of the compound. Means whether it is dextro or LIGO, these capital D and capital L have nothing to do with it. It's only the plus and the minus signs which will represent the dextro and the LIGO-rotatory nature of any particular molecule. The meaning of D and L notations are basically like the letters D or L before the name of any compound will indicate the relative configuration of a particular stereoisomer. This refers to their relation with a particular isomer of glyceraldehyde. So when we talk about the structure of glyceraldehyde is basically having one asymmetric carbon atom and it exists in two enantiomeric forms. So plus glyceraldehyde and minus glyceraldehyde. So if you see there, what is the structure of glyceraldehyde? CHO, CHOH, CH2OH. So if you look at the middle carbon atom, that is actually asymmetric or chiral in nature. When we have OH present on the right hand side, it is going to be plus because it is dextrorotatory. And when we have OH present on the left hand side, it would be minus because it is levorotatory. Now, Plus and minus for glyceraldehyde are same as plus and minus for glucose. Okay, one is plus means dextro, minus means LIGO. But where are the capital D and capital L in glucose coming from? That is coming from their configuration with respect to the glyceraldehyde molecule. Now, if the glucose is named as D, it means that it is going to be having the same configuration as plus of glyceraldehyde. Okay. So remember that D and L have no relation with the optical activity of that compound, but these capital D and capital L have a relation with the optical activity of glyceraldehyde. So capital D before the name of glucose represents the configuration plus, that is the dextrorotatory nature of glyceraldehyde, and when we have L, it would be the minus of glyceraldehyde. Okay, so this is D plus glyceraldehyde, and similarly we have in case of D plus glucose, and similar is going to be the case with L. So let's quickly have a look at few MCQs. Reaction of acetic anhydride with glucose indicates what? Now, when we have the reaction with acetic anhydride, remember all the OH groups are going to get converted into the acetate groups, right? And that is actually going to tell us that there are 5 OH groups which are present in the glucose molecule. So option, wait, acetic anhydride is not an oxidizing agent. I think option A should be the correct answer. We have already discussed that part. Okay, so whatever reagent we have used for getting glucose pentaacetate, if it's acetic anhydride that we have used, then option A should be the correct answer. Otherwise, option C is the correct answer. Next question is, correct representation of glucose is D plus glucose, D minus glucose, D glucose, or D L plus glucose. So we have already seen the structure of glucose, and the correct representation is D plus glucose. Option A is the correct answer. Next, we move on to part 3 of preparation and structure of glucose. Now, glucose has got a cyclic structure. Now, you will say we have just studied that it is a straight chain molecule and all the 6 carbon atoms are attached to each other in a straight chain. How come it has got a cyclic structure? Now here, the structure 1 of glucose which explained most of its properties, but the following reactions and facts would not be explained by this structure. The first one was, despite the presence of an aldehyde group, glucose does not give 2,4-DNP test or Skiff's test, and it does not does not form the hydrogen sulfide addition product with sodium hydrogen sulfide. Now, why is that? Because the acetaldehyde group, that is CHO group that is present, is actually not present as CHO. Okay, we'll just have a look at the cyclic structure. Secondly, the pentaacetate of glucose does not react with hydroxylamine, indicating the absence of free CHO group. That's what I told you. Therefore, glucose is found to exist in 2 different crystalline forms named as alpha and beta. The alpha form of glucose has a melting point of 419 Kelvin and is obtained by the crystallization of concentrated solution of glucose at 303 Kelvin. So this is alpha glucose. This is the cyclic structure of glucose that I was talking about. So what you have, if you carefully see. Now here, this is the first carbon atom, which is the aldehydic group here, which is not actually the free aldehyde group. It is actually CHOH. Then this is the second carbon atom, CHOH. CHOH third carbon atom, CHOH fourth carbon atom, CHO. So this is the fifth carbon atom, and this is sixth CH2H. Now, if you look at the fifth carbon atom, there is CH present, but this OH has actually, from here, H has actually gone, and this is linked to the first carbon atom. So there is this cyclic structure that we obtain. While the beta form, which has a melting point of 423 Kelvin, is obtained by the crystallization of hot and saturated aqueous solution at 371 Kelvin. Now, this is the beta form. You will realize that there is a difference in the alpha and beta structures based upon the positioning of the OH groups. These 2 cyclic forms exist in equilibrium with open chain structure. Okay, so alpha form, beta form, and the open chain structure, all these are in equilibrium with each other. You cannot say at what point of time this particular structure is going to be present and at what point of time another structure of glucose is going to be present in solution. So it may be proposed that one of the OH groups may add to the CHO group and form a cyclic hemiacetal structure. This behavior could not be explained by the open chain structure. So this is the open chain structure where we have the aldehyde group present, and this is the alpha D glucose, okay, and this is the beta D glucose. So if you see, alpha form would be the one where the OH is present downwards on the first carbon atom, and beta form is the one where OH is present upwards in the on the first carbon atom. That is towards oxygen is the beta form and away from oxygen is the alpha form. Okay. And why is it called hemiacetal form? Because half of the acetaldehyde group has actually disappeared from here. It was found that glucose forms a six-membered ring in which OH at carbon 5 is involved in ring formation. This explains the absence of a free CHO group and also the existence of glucose in two forms. So here you can see the first carbon atom and the fifth carbon atom are actually getting connected together through this oxygen atom, forming a six-membered ring structure. So we have alpha D glucose where, the OH is going to be present towards oxygen, right? And the other is the beta form of it, where, this is the straight chain form of it, and the beta form is where OH is going to be present away from this oxygen. So this is beta D plus glucose. Pyran is a cyclic organic compound with one oxygen atom and 5 carbon atoms in the ring. This is the structure of pyran. Now, the cyclic structure of glucose is more correctly represented by the Hayward structure. Now, what is Hayward structure? Instead of, this straight chain form and showing a ring with the first carbon atom connected to the fifth carbon atom, we can actually represent it in this hexagon form, which is known as the Hayward structure, where when the OH is present towards oxygen, okay, so it is not correctly represented. This OH should actually be coming down, okay. So this is, just make this correction here, this OH is downwards. So this downwards OH is actually representing the alpha form and this is the beta form. In between there is a straight chain structure, showing that all these three forms are going to exist in equilibrium with each other. Now, how is this cyclic structure being formed? What happens is the lone pair of electrons that is present on oxygen is going to attack this sp2 hybridized carbon, which is actually electron deficient because of being sp2 hybridized. Okay, so when this attacks onto here, then this double bond shifts here, giving a minus sign here, and this hydrogen is then going to be accepted by this minus sign, forming OH here, and a bond will form between oxygen and carbon here. I hope this is clear how we get the cyclic form. This is the Hayward structure of glucose. Now, what are anomers? Anomers is a very important term when we talk about stereochemistry. So, the two cyclic hemiacetal forms of glucose differ only in the configuration of the hydroxyl group at C1. We have seen, okay, that when it is present away from the oxygen atom, which is connecting the fifth and the first carbon atoms, when OH group is away from it, it is alpha, and when it is towards it, it is beta. So that means only at the first carbon atom, the configuration of the hydroxyl group is differing, and this means that these two forms are actually anomeric forms, or these are anomers. Okay, that means, and C1 is going to be called as the anomeric carbon, which is the aldehyde carbon before cyclization. So this is how you can see here. Then such isomers, that is alpha form and beta form, are called anomers. The six-membered cyclic structure of glucose is called pyranose structure in the analogy of pyran. Okay, so this is pyranose structure because it is similar to the structure of pyran that we have already discussed. Since OH is at the first carbon atom is away from oxygen, it is alpha D plus glucose, and this is beta D plus glucose. Now, anomers is one term. Let us now discuss about epimers. Now, they are diastereomers that contain more than one chiral center but differ from each other in absolute configuration at only one chiral center. Okay, so that means there are more than one chiral centers which are present in the molecule, like we have here. This is also chiral, this is also chiral, this and this. All these four carbon atoms are chiral carbon atoms. But if you see for the rest of the carbon atoms, Here also OH on left, OH on left, OH on right, OH on right, OH on right, OH on right. So for the rest of the 3 carbon atoms, the configuration is the same. But if we look at the first chiral center, OH is on right, here OH is on left. So when they differ, okay, when they have more than 1 chiral centers, that's the first condition. Second condition is when they are going to differ in configuration at just 1 chiral center, then these two are going to be called as epimers. The first one is D-glucose. The second structure is known as D-mannose. Okay, both of them are not glucose. The moment you have OH group shifted to the left hand side on the first chiral center, it is no more glucose. It will be called as mannose. But D-glucose and D-mannose are examples of epimers. Let's quickly have a look at few MCQs. Anomers differ at second carbon, fifth carbon, first carbon, or third carbon. So when we talk about glucose, anomers means they differ at only 1 carbon atom, which is actually the first carbon atom. So option C is the correct answer. Next question is pyranose is a 6-membered ring with 6 carbon atoms, 5-membered ring with 5 carbon atoms, 6-membered ring with 5 carbons and 1 oxygen, or 5-membered ring with 4 carbon and 1 oxygen. So we have already seen that pyranose is basically a 6-membered ring in which there are 5 carbon atoms and 1 oxygen atom is also present, which is a part of the ring only. So option C is going to be the correct answer. So this is all about the preparation and structure of glucose that we had to take up in this lecture. I am again telling you that you do not have to cram anything. All that you have to do is understand these things. Please practice drawing the structures a lot many times, because the more you get to know the structures, the more simpler or easier it becomes for you to actually write down the reactions on your own without learning or cramming them. Okay. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app through Google Play Store or App Store for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.